Hello everyone. So in this video we will be seeing balancing of rotating masses. So as we all know that in machines there are many rotating and reciprocating masses. If these rotating and reciprocating masses are not properly balanced, so then they will generate some unbalanced forces as well as unbalanced couples. And if you look at these unbalanced forces and unbalanced couples, so these unbalanced forces and unbalanced couples are dynamic in nature. So when the machine is subjected to these dynamic loads, the machine will be vibrating. So as a result of these vibrations, running life of the machine will come down. So just to overcome this, so just to increase the running life of the machine, or to run the machine smoothly without any noise and vibration, so what we do is we go for balancing of these rotating and reciprocating masses. So if I have a system in which these rotating and reciprocating masses are completely balanced, so even though the machine is running, there won't be any vibrations inside this machine. Now here, so we will be seeing balancing of rotating masses. So for balancing of rotating masses, there are two different techniques. So one is a static balancing and second one is dynamic balancing. So here in this video, we will be discussing static balancing. So what is static balancing and what is dynamic balancing? Whenever I say static balancing, so there should not be any resultant force inside the system. And whenever I say dynamic balancing, so there should not be any force as well as couple. So if there is no resultant force inside the system, so we say that is statically balanced. So if there is no force as well as there is no resultant couple, so we say the system of rotating masses are dynamically balanced. So here the system of rotating masses are statically balanced and here the system of rotating masses are dynamically balanced. And here if you look at this balancing, static balancing, we use this technique so when the masses are rotating in the same plane. And we use this dynamic balancing technique when the masses are rotating in different planes. So if I take a case like this where the masses are rotating in the same plane, if I take the masses rotating in the same plane, so when the masses are rotating in the same plane like this, so there will be forces in the same plane. So whenever there are forces in the same plane, there won't be any couple produced due to these forces. Whereas, so when the masses are rotating in different planes like this, so there is one mass rotating in this plane and there is one more mass rotating in this plane. Whenever the masses are rotating in different planes, so you can see they will be producing centrifugal forces in respective plane. The forces are in different planes. As a result of this, so there will be couple produced in this direction. And as the shaft is rotating, the direction of this couple will be continuously changing. So here, since the masses are rotating in the same plane, there is no unbalanced couple. We don't check for couple. So there are only forces. We check for forces. If forces are balanced, in this case, we say everything is balanced. So here, there are forces as well as couple. Therefore, we check both forces and couples. So whenever the masses are rotating in the same plane, we go for static balancing. And whenever the masses are rotating in different planes, we go for dynamic planes. We go for dynamic balancing. So I can take an example. If I take a fan, so in the fan there are three masses, and the three masses are rotating in the same plane. So there we go for static balancing. And if I take a crankshaft, in crankshaft there are different masses. I can say different cranks on the crankshaft, and these cranks are in different planes. So whenever I design a crankshaft, I go for dynamic balancing of this crankshaft. So in this video we will see static balancing. So for doing this static balancing, so I am considering a system like this. I am considering a system of rotating masses. So let me say, so there are some three masses rotating on this shaft, and the three masses are in the same plane. So I am considering three masses. So M1, M2 and M3. So there are three masses and three masses are rotating in the same plane like this, exactly like your fan. And I am assuming, so these three masses are rotating at some radius R1, R2, R3. So radii of rotation are R1, R2, R3. And I am assuming these three masses are rotating in the directions, so theta 1, so theta 2 and theta 3. So I consider three masses, and these three masses are rotating at radii R1, R3, and in the directions theta 1, theta 2, theta 3. So when the shaft is not rotating, there is no problem. When the shaft is not rotating, the shaft will be subjected to this gravitational force. I mean the bearings will be subjected to only static force. Gravitational force is a static force. So problem comes when the shaft is rotating. So when the shaft is rotating with some angular velocity omega, you can see this mass is rotating, so this will generate a radially outward centrifugal force, so of magnitude m1 r1 omega square. And here, so this mass will also generate a centrifugal force in radially outward direction. Magnitude of this force I am calling it as F2, that is M2R2 omega square. And this mass will also generate a centrifugal force in radially outward direction, that is M3R3 omega square. I am calling this as F3. So when the shaft is rotating with some angular velocity omega, so these three masses will generate centrifugal forces in radially outward directions. Now see here, there are three forces acting on the shaft. So the resultant of these three forces, if it is zero, we say there is no unbalanced force acting on the shaft. Therefore I can say there won't be any force on the bearing. So the problem comes when these forces are not balanced. So if I go for vector addition of all these forces and I found that there is some resultant force. So whenever there is some resultant force acting on the shaft, as the shaft is rotating, the direction of this force will be continuously changing. Therefore I can say the shaft will be subjected to dynamic loads, whereas the bearing will be subjected to dynamic loads. If the bearing is subjected to dynamic loads, the entire machine starts vibrating. So due to this, running life of the machine will come down. So to overcome this, we need to balance this. So for solving this problem, so there are two techniques. One is the graphical method and second one is analytical method. In graphical method or analytical method, we do only two things. One, what we do is, we find the resultant force acting on the shaft. If we found that there is no resultant force acting on the shaft, we say the system is balanced. If there is some resultant force or resultant unbalanced force acting on the system, so we try to balance this resultant unbalanced force. Now see here. So I can say like this, there may be some case so where the vector addition of all the three forces F1 bar plus F2 bar plus F3 bar, so vector addition of all these three forces is 0. If vector addition of all the three forces is 0, we say the system of rotating masses are balanced and no need to do anything. And we will assume a case where so vector addition of these three forces is non-zero. So I am solving by graphical method. Now you can see here, so when the shaft is rotating with some angular velocity omega, this mass 1 is producing a centrifugal force in this direction, mass 2 is producing a centrifugal force in this direction, mass 3 is producing a centrifugal force in this direction, and all the three forces are in the same plane. So I am going for vector addition of all the three forces. Now you can see due to mass 1, so there is a centrifugal force in this direction. So draw a vector, so parallel to the force vector. So due to mass 1, there is a centrifugal force in this direction. So length of this vector indicates magnitude of that particular force. So this is nothing but F1, that is M1, so R1, so omega square. And you can see, due to mass 2, there is a centrifugal force in this direction. Due to mass 2, there is a centrifugal force in this direction. There is a centrifugal force in this direction. So length of this vector is equal to magnitude of the force, so M2 R2 omega square. And you can see, due to mass 3, there is a centrifugal force in this direction. I am drawing a vector parallel to that line. So due to mass 3, there is a centrifugal force in this direction. So this is centrifugal force. Length of this vector is equal to, so magnitude of the centrifugal force, M3R3 omega square. So you know the mass that is present on the shaft, and you know the radius at which it is rotating, and you know the angle. So therefore I can say magnitude of the vector is known, direction of the vector is known. Therefore I have drawn three vectors. This is vector 1. So at the end of this vector I place the beginning of second vector. At the end of this vector I place the beginning of third vector, and so on. So this is nothing but vector addition. So the closing side will give the resultant of force that is acting on the shaft. The closing side, that is from the beginning of first vector to the end of last vector. So from the beginning of first vector to the end of last vector, this gives you magnitude and direction of the resultant force that is acting on the shaft. So here at this instant, so the shaft is subjected to a resultant force of magnitude equal to length of this vector in this direction. So you know the resultant force that is acting on the shaft at this instant. Now what I do is, I make an arrangement inside the system. I modify the system in such a way that I can generate a force of same magnitude but opposite in direction. So what I do is, so I make an arrangement inside the system such that I can generate a force of same magnitude but in the opposite direction. So if I can generate a force of same magnitude but opposite in direction, then the new system, so there won't be any resultant force. So to generate a force of this magnitude in this direction, what I do is, so I add a counter mass on this particular shaft. I add some counter mass on this shaft at some radius RC. So as I know the direction of the force, so I will introduce this counter mass in the same direction. So I am calling this as theta c. So I will introduce this counter mass in the same direction, that is theta c. I introduce this counter mass in such a way that, so when the shaft is rotating, this counter mass will generate some centrifugal force. Magnitude of this centrifugal force is mc rc omega square. So I introduce mass in such a way that, so the centrifugal force produced due to that mass is equal to this length, I can say. So I make an arrangement inside the system such a way that it can produce a centrifugal force of this much magnitude. So to produce a centrifugal force, I need to introduce a counter mass. Now I introduced a counter mass. Now if you look at the new system, that is modified system, so earlier there were only three masses, there are three forces, and the three forces were not balanced. Now what we did is, so we introduced some counter mass, and this counter mass is also producing some centrifugal force. Now you can see now the new system is having four forces, there are four masses, and due to these four masses there are four forces. And you can see the vector addition of four forces, you are getting a closed polygon. It means, so the resultant force acting on the shaft now is 0. So therefore I can say the system of rotating masses are balanced. So you know this force, so you know the length of the vector, so length of the vector gives you mc rc omega square. Omega is the speed of the shaft that is already known to you, so I can say like this, length of this vector gives you mc rc. mc rc is nothing but length of the vector. So if you choose mass, counter mass, what to be placed, you will get the radius at which you need to place. Or if you choose the radius at which you need to place the counter mass, you will get the counter mass what you want to place. Or I can say if I want to place some 2 kg mass at some 5 cm radius, or I can say I can place 5 kg mass at 2 cm radius. If you choose radius, you will get the mass, and if you choose the mass, you will get the radius. You need to choose at least one of these two. And the direction, so is given by direction of the vector. So angle is measured with reference to some x-axis. So here also I am measuring the angle with reference to the same direction. This is theta c. So once you can find length of this vector, so you can find the counter mass that is to be introduced. Once you introduce the counter mass, the system of rotating masses are balanced. This is graphical method. Now we will see the analytical method. So I am considering a shaft, so which is having 3 rotating masses. I am considering a shaft which is having 3 rotating masses in the same plane. So there are 3 masses, M1, M2 and M3. So these 3 masses are rotating at the radii R1, R2, R3 in the directions, so theta 1, theta 2 and theta 3 like this. I am assuming speed of the shaft is some omega. Speed of the shaft is some omega. So there are 3 masses, and 3 masses are rotating in the same line. So the shaft is rotating with some speed omega, so this mass will generate a centrifugal force in radial outward direction. That I am calling it as M1, so R1 omega square. So this mass will produce a radially outward centrifugal force, so that is F2, so M2 R2 omega square. This mass will also produce some centrifugal force, F3, that is, so M3 R3 omega square. The 3 masses will produce some centrifugal forces in radially outward direction. So by analytical method, so I want to see whether the system is balanced or not. If it is balanced, then nothing to do. If it is not balanced, we will try to balance it. So what I do is, so I know the 3 forces, I can say like this, so if summation of forces is 0, so I can say summation of their components will also be 0. I take the components along x direction, and I take the components along y direction. So if I find that the component along x direction and y direction are balanced, so I say there is no resultant force acting on the shaft, and I say the system of rotating masses are balanced. So if I found that, so summation of component of forces in x direction is non-zero and y direction is non-zero, it means that it's not in equilibrium, there is some resultant force acting on the shaft. There is some resultant force acting on the shaft. So it means that the system of rotating masses are not balanced. So here there are 3 masses, and I am assuming, so the system of rotating masses are not balanced. If they are balanced, so there won't be any x component of force or there won't be any y component of force. So I am assuming, so summation of all the 3 forces is non-zero. So vector addition of all the forces is non-zero. Vector addition of all the forces is non-zero. It means that so the system of rotating masses are not balanced. So what I do is, so there are three masses and these three masses are not balanced. These three masses are producing three forces and the three forces are not getting neutralized among themselves. So what I do is, so I introduce some counter mass inside the system such that this counter mass will produce some centrifugal force. So already there are three forces and the centrifugal force that is produced due to this counter mass will balance the forces. I can say like this, so what I am doing is, so I am introducing some counter mass MC at some radius RC. And now it is generating some centrifugal force MC RC omega square in some direction like this. So I am assuming the direction is some theta c. It is generating some centrifugal force like this. Earlier there were three forces, the three forces were not neutralized. So I am introducing one more force inside the shaft in such a way that after introducing this counter mass, so vector addition of all the forces is zero. So earlier there were three forces, so F1 plus F2 plus F3. So F1 bar plus F2 bar plus F3 bar, this is non-zero. So it's not balanced. The system of rotating masses are not balanced. To balance this system of rotating masses, what I am doing is I am introducing a counter mass. I can say like this, after introducing counter mass. So after introducing counter mass, summation of forces is zero. It means that, so now there are four forces, force produced due to mass 1, force produced due to mass 2, and force produced due to mass 3, and the counter mass is also producing some centrifugal force. Now there are four forces and these four forces are getting neutralized among themselves. Now see here, if summation of forces is zero, I can say summation of their components will also be zero. So it means that if you take summation of components along x direction, it must be zero, and summation of components along y direction must also be zero. Now first I am taking the components of forces along x direction. You can say this force is F1, it's making an angle θ1 with respect to x axis. So if I take component of this force along x direction, it is so m1, so r1, so omega square cos θ1 plus this mass 2 is making an angle θ2 with respect to x axis. I can say, so component of this force along x direction is m2 r2 omega square cos θ2. m2 r2 omega square cos θ2. And mass 3 is making an angle, so θ3, m3 r3 omega square is the force, and cos θ3 gives component of this force along x direction. And this force mc is making an angle θc, mc rc omega square cos θc is equal to 0. So component of force along x direction is 0. Now I can eliminate this omega square. I am eliminating this omega square which is common in all the equations. It's 0 there. So here you can see this term, it is m1 r1 cos θ1 plus m2 r2 cos θ2 and so on. I can write it simply like this. It's a summation of mr cos θ plus mc rc cos θc. This is 0. So I can simplify this like this. I am making this mc rc cos θc is equal to minus summation mr cos θ. So earlier there were three forces. These three forces were not neutralized among themselves. So to balance this, what I did is I introduced some counter mass. After introducing this counter mass, the resultant force becomes 0. So I don't know what is the counter mass that I have to introduce that. So, but I introduced some counter mass and the forces became 0. So it means that I am introducing some counter mass. I don't know that. So I want to find out that. So I introduce this counter mass in such a way that the forces are getting neutralized. MC is a variable, RC is a variable, and θc is a variable. I need to find out these values. So I am finding out these values. So I made MC, RC and cos θc as a subject. So if I take components along x direction, I got this equation. I am calling this equation as equation number 1. So similarly, so if I take components so along y direction, it's making θ1 with respect to x axis. I can say with respect to y axis, it's 90 minus θ1. I can say it's cos 90 minus θ1 is sin θ1. So I can write like this. If I take components along y direction, similarly taking components along y direction. So if I take components along y direction, I will be getting mc rc sin θc is equal to minus summation mr sin theta. If I take components along y direction, I will be getting this equation. By solving these two equations, we can find the counter mass what is to be introduced and in which direction we need to introduce the counter mass. So I am solving these two equations. So I am going for squaring and adding of both the equations. So 1 square plus 2 square. So from here I can write like this: MCRC is so under root. So summation mr cos theta whole square plus minus summation mr sin theta whole square. So if you go for squaring and adding of both the equations, here it is MCRC cos theta c whole square plus MCRC sin theta c whole square. If I take out MCRC whole square, it's a sin square theta c plus cos square theta c is 1. I have sent the root actually. So here in this equation, so you will get the product MCRC as some value. So it means that if you choose radius, so you will get the counter mass what you need to introduce. If you choose the counter mass, you will get the radius at which you need to introduce. So if radius is given, you can find counter mass. If mass is given, you can find the radius at which you need to introduce the counter mass. You need to choose at least once. One. Or MC or RC. Now from these two equations we can find the direction in which I need to introduce the counter mass. So if I go for equation 2 divided by equation 1, so I can write like this: tan theta c is minus summation mr sin theta, so divided by minus summation mr cos theta. So from here you can find the value of theta c. So now you know the value of counter mass and you know the direction in which you need to introduce the counter mass. So by introducing the counter mass in that particular direction, you can balance the system. So now if you find the resultant force, there won't be any resultant force inside the system, and this way we can balance these rotating masses. And here you don't cancel this negative signs in the numerator and denominator. The negative signs of numerator and denominator will indicate the quadrant in which I need to place the counter mass. So I can say like this: if numerator is positive and denominator is also positive, we need to introduce the counter mass in first quadrant. If numerator is negative and denominator is positive, I can say sin negative and cos positive. So I can say we need to introduce in fourth quadrant. So if both are negative, so we need to introduce, numerator is negative and denominator is negative, we need to introduce the counter mass in third quadrant. If numerator is positive and denominator is negative, we need to introduce the counter mass in second quadrant. So based on the signs of numerator and denominator, so we need to introduce the counter mass in respective coordinates. Thank you.